Hi, and welcome back to Computer Science Theory. This is Comms 3261, Summer B 2021 at Columbia University. And this is Lecture 3, Part 2 on the regular expressions. So the idea here, we're going to go off in a different direction from what we've been doing so far. So far, we've been talking about languages, and we've been talking about automata, little machines for recognizing languages. Every automaton will let you feed in a string or read a string somehow, and then give you some sort of output on that string. Regular expressions also have to do with languages, but they're a little bit different. In particular, they're ways for succinctly expressing languages. They're little expressions that will evaluate to a set of strings. So, idea is that we can use the regular operations that is union, concatenation, and star to build up expressions describing languages. And you may have seen these before, may have seen regular expressions, maybe not introduced in this way, but if you've used, you might have seen them in programming, you might know them from Unix, like you might have fed regular expressions into Unix programs, which can parse them. Here's an example of a regular expression. 0, union 1, O, 0 star. And I'll just annotate this. Whenever we write a string in a regular expression, a string of alphabet symbols, so I guess implicitly the alphabet here is the binary alphabet, as usual. This means the language just containing that string, the string 0. Likewise, this is the language just containing the string 1. If you take the union of those two things, you get an expression which is the language containing the string 0, union with the language containing the string 1. Whenever we write two strings next to each other, we imply concatenation. And then when we use the star expression works just like it's worked before. So this last chunk means 0 or more concatenated zeros. So I'm going to go through all of these specific operations in more detail, but you may recognize this right off the bat. And how you would read this in English maybe is either 0 or 1. That's our first language. That's the union bit, followed by some number of zeros. So this language contains it contains 0, 0, for instance. 1, 0, that's a 1 followed by some number of zeros. 0 or 1, just those strings, because they start with a 0 or a 1. They're followed by some number of zeros, none of them. You also have 1, 0, 0, 0, 0, 0, some number of zeros. A string that would not be in the language, for instance, 1, 0, 1. This string does start with a 1. That 1 is followed by a number of zeros, but there is a 1 concatenated at the end. So this string is not in the language that the regular expression we've written above evaluates to. So definition, we say that a regular expression evaluates to the language it describes. So, you know, this regular expression above, 0 union 1, you could just write an equal sign and then define the language. So what we'll be doing today, we will be writing down regular expressions. We will be talking about going back and forth from, getting very comfortable with the language, going from regular expressions to languages, languages to regular expressions. This is, again, these operations we're using are just union, concatenation, and star, the same 3 operations we've just used and talked about in the earlier parts of this lecture and last lecture. We're just writing them in this abbreviated form. Another example. What if I just wrote 0 or 1 to the star? Well, the 0 union 1 is just either a 0 or a 1, and then either a 0 or a 1 repeated some number of times. This is a very important language. This is the language of all binary strings. So in a short amount of space, you can describe some pretty big languages. Of course, I owe you a formal definition. I can't just leave it undefined. And this is actually a really interesting formal definition. So unlike some of the ones where we'll hurry through and say, well, I've been using this word evaluate, it means precisely what you think it might mean. This one is interesting for its structure. So in itself, this definition has some cool content. So definition, regular expressions, formally. And the idea here is that we'll define inductively as in because regular expressions can be long and complicated, we'll recursively describe how to build one. So we say that R is a regular expression if it meets one of these 6 conditions. So the first type of regular expression R is just a single symbol from an alphabet. And, we've talked about that. That just notes the language containing only that alphabet symbol. That's a very simple regular expression, one of our building blocks. Similarly, we define the empty string to be a regular expression. So that's just the language containing only the empty string. And our last simple case, thanks, by the way, to the person who told me, don't write on the lines. It's a huge pain when you're downloading the notes. The last basic building block, have I already done it? No. Okay, here's our first line of the day. I think the goal will be to get through this lecture writing on maybe, call it one or fewer lines. I'll give myself one mistake. Finally, we can have the language containing no strings. So those are our basic building blocks. And if we go on like this, it's going to take us an infinite number of lines to define every possible regular expression. So we define a regular expression to be any one of these things and also any combination of other regular expressions made in these three ways using the regular operations. So we'll also say R is a regular expression if it's the union of two other regular expressions, or if it is the concatenation of two other regular expressions, or if it is the star of some other regular expression. And this finishes the definition. Why does this capture all regular expressions? Well, you can kind of see if I write down, for example, our regular expression from before, that it breaks down into regular expressions in the same way. So, right, if this is our regular expression R, then, well, it's really just two regular expressions concatenated together. It's 0 union 1 concatenated with R2, which is O star. And this is just a regular expression 3 with a Claney star. And this is just, call it R4 will be 0 and R5 will be 1. So we can see how the regular expression we used earlier fits our inductive definition, because at every step, well, our first R decomposes into two regular expressions. So here we're using case 4. Then 0 union 1 decomposes into two regular expressions. Oh, sorry, we're not even using case 4. First time we're using concatenation. Then we can decompose this again using the union case. Similarly, we're using the Claney star case over here. In this definition, you can tell it's not circular, because every time you do a recursive definition, every time you essentially call deeper into your definition, your regular expression gets smaller. So if I wanted to take a regular expression or something that someone had told me was a regular expression and try to evaluate it to see if it fit the definition, I could recursively break it down and be confident that my pieces would be getting smaller every time until eventually I reached one of my base cases. So this is an inductive definition. Neat little cases, but it'll let us build big things. I'm also going to give you a few more bits of notation that we'll use as shorthand when we're writing down regular expressions. So these are things that you could in principle write out in full, but they'll let us write our regular expressions more compactly. They're not really new operators, they're just new notation. So some shorthand for regular expressions. If I write the symbol sigma, that's short for any symbol in the alphabet. So as an example, if I'm using the alphabet sigma equals 0, 1, which I don't have to use, by the way, I can use any alphabet with regular expressions, then sigma is just shorthand for 0, or 1. And you can imagine with a long alphabet, it's more helpful to write sigma to mean anything in the alphabet than doing a giant union expression every time. R plus is defined to be 1 or more copies of R concatenated. If you want, you could also note that R plus is equal to R concatenated with R star. That is at least 1 copy of R concatenated with 0 or more copies of R. So R plus will just mean we want at least one of those things, whereas the Kleene star always includes the empty string as part of the new language we get. And then finally, for any natural number k, we write R to the kth power to mean k copies of R concatenated together. So for example, if I wrote 0, 1 to the 3rd power, that's just short for 0, 1 concatenated with 0, 1 3 times. So those are our shorthand notations. Again, like if you wanted to, you could never use any of these when you're writing out regular expressions. You just write slightly longer regular expressions, but they'll be handy and they'll be coming up. So we'll keep seeing these. Our final note on evaluating regular expressions is order of operations. If in doubt, you can always use parentheses to tell me where to evaluate the regular expression first. So for example, I just wrote 0, 1 to the 3rd power. I put 0, 1 in parentheses to indicate that I concatenate 0 and 1 before I do the 3rd power operation. If in doubt, parentheses always make things clear. But if they're not specified, you do it in this order. First, you do Kleene star. Second, you do concatenation. And third, you do union. So for example, if I have 0, union, 1, concatenated with 0, Kleene star, I would first evaluate Kleene star, call it 0, 0, 0. And then I'd evaluate the concatenation. And then I would do 0 or that. And then I suppose my output could be 0, could be 1, 0, 0, 0, could be something else. Usually, instead of writing this, you would put the union in parentheses because this is a little bit unclear. But perfectly well defined in terms of order of operations. As a reminder, when in doubt, just use parentheses. Okay, so at that point, this completes the definition of regular operations. For the remainder of this segment of the lecture, I'm just going to do a bunch of examples, and then we'll move on to proving some things about these. Let's see. 0 star, 1, 0 star. Oops, not 0 to the 1. And every time I'm going to do one of these, I'm going to pause for a few seconds to simulate some in-class interaction. If you want, just think in this little chunk of time, okay, what do I evaluate first? If you have enough time to get there, try to think about what is this language? While I've been filling time, maybe you've evaluated this language for yourself. This is the string of regular expressions, or sorry, this is the language W, where W contains a single one. Because we've got 0 or more zeros, then a 1, and then 0 or more zeros again. And that describes every string that contains a single one. Here's another one. 1 star, 0, 1 plus. That is supposed to be a plus sign, star. I think I'm going to write this out in a slightly longer form first, although there's a cleaner way. So you could say W, and this is a perfectly reasonable thing to do on homework or when you're trying to write out a regular expression, is write out a more complicated description of the language and then see if you can boil it down to something conceptually simpler. When I say conceptually similar, there's no formal definition behind that. But occasionally it's nice to have a few words or remember what's going on. So this is the language. You could call this the language of all strings of 0 or more ones. I'll write out the word 0 so there's no confusion. Followed by 0 or more substrings consisting of 1, 0, and 1 or more ones. And I think this is correct. A more concise definition, you could say W is the language in which it's all strings W such that every 0 is followed by at least 1, 1. And why is that equivalent? Well, if you look at this regular expression, it can start with some number of ones or no ones at all. Really, the only hard rule going on here is every time I see a 0, it has to come from this second expression, 0, 1 plus, and it always has to be followed by at least 1, 1 before another 0 can come along. And if you wanted to double check that this language was indeed what the regular expression evaluates to, you could observe that any string you can write down, which meets this description, can be generated by this regular expression, just by chopping up the string into substrings, starting with zeros. So first couple of examples. What about sigma, sigma, sigma star? So if we recall sigma as our shorthand notation, it means plug in any symbol from my chosen alphabet. So in this particular case, it doesn't seem like the symbol I choose matters much. And this is the language of all strings that have length multiple of 3. Of course, I could have written that for length of W if I wanted to. So this just tells me it could be the empty string, because that's property of Claney star, and then it's just 3 symbols from the language, and it's strings of 3 symbols from that language. Strings of 3 symbols from the alphabet concatenated some number of times. Okay. O sigma star O union 1 sigma star 1 union O union 1. So if this looks a little baffling, might help to start by just breaking it up using what we know about order of operations. We scroll up. Our order of operations tells us that union comes last. So in particular, we can break this into a bunch of chunks, 4 chunks, and then know that we're going to evaluate the union at the end. So this is just the language of any regular expression that meets these 4, any one of these 4 criteria, or more of these, one or more has to be true. So 0 or 1, or any string that starts and ends with a 1, or starts and ends with a 0, and has 0 or more characters in between. So this is just the language of all strings that start and end with a 1 or a 0. All the strings on the alphabet 0, 1 that start and end with the same character. And you note that if we didn't have this extra little bit at the end here, if we didn't add 0 and 1 to our language, this wouldn't have been quite true, because our first 2 expressions don't allow the string 0 and the string 1, right? This first regular expression, 0 sigma star 0, has to have at least 2 zeros in it on either side of this intermediate term. So that's why we've added those 2 things on at the end to really capture the concept we mean. Okay, what about 0 or empty string concatenated with 1 or empty string? So this is a finite language, and rather than writing it as I've written these other languages as all W that meet these restrictions, I'm just going to write out every string in the language. So in particular, my string starts by concatenating a 0 or the empty string to a 1 or the empty string, which gives me the possibilities 0, 1, if I concatenate a 0 with a 1, epsilon 1, which is just 1, if I concatenate epsilon and 1, 0 epsilon, which is just 0, if I concatenate 0 with epsilon, and finally empty string, if I concatenate epsilon with epsilon. So that's my finite language. Yeah, easy to write it out as 4 strings. Couple more here. 1 star null set. So if you recall, this is the symbol that denotes the language with no strings. And this is actually defined to be equal to null set or empty set. The reason being that this expression is concatenating 2 things together. A 1 star, so a string of 0 or more 1s with the empty set. And the logic here might make more sense if you think about it as we pick a string from the language 1 star, and we concatenate it with a string picked from the language that doesn't contain any strings. Whenever we concatenate with the empty language, we get the empty language because there's nothing to pick, no string to concatenate with. Oh, caught myself. I'm not going to write on the line today. Similarly, like arbitrarily defined, the Kleene star of the null set is just the set containing the empty string. So if you pick 1 or more things, 0 or more things from the empty set, you get the empty string. This is a little bit maybe confusing with the one above. If it does confuse you, I'd encourage you to just memorize these base cases because there's only 2 of them. Often when there's sort of odd cases defined at the edge of a formal system like this, they're defined because they make other parts of the system work more smoothly. So we've got these last 2 things that might be worth bulleting down. Okay, one more regular expression, then we'll wrap this bit. Just to show you what you can do with alternative alphabets or multiple sets of symbols, you could have, say our alphabet is no longer 0 and 1. Maybe it's dash, period, 0, 1 through 9. So the decimal alphabet plus a couple of extra symbols. And we'll define D to be the subset of our alphabet 0 through 9. Then the regular expression, empty string, or dash, concatenated with D plus, or 0.D plus, or D plus, point D plus. This is going to be set of floating point numbers as you would normally write them. So numbers like 103, negative 92.9, 48.666, 0.1, etc. So the first part is telling us our number can be negative or it can be positive, which we denote by not putting a negative sign in front of it. And then it can have one of these three formats. It can be a number like 103, which is just one or more decimal digits. It can be 0 point something, or it can be some number point something. Strictly speaking, I just wrote this out quickly as an example. I don't think I need this middle term. I've overly complicated my regular expression because you can make 0 point D plus with D plus point D plus. So yeah, you can make it that much simpler. The first regular expression would also have been correct. It was just redundant. But there's a catch. And you can, of course, get much more complicated than this with regular expressions. So hopefully that went fairly well. If not, there's tons of these to work out in the exercises section of the textbook. And in the next subsection, we will talk about converting regular expressions to NFAs. So they're no more powerful than the automata we've seen so far in terms of the language they represent. Thanks for listening. See you in the next part.